Our infrastructure, the initial product offering relied heavily on public APIs for transactions. There's services like Parbrink and Toast that we can ping via API to get that data, and cloud accessible cameras that we could pull footage from and import into our cloud. As we look to expand our customer base, getting into private firewall networks became a hard requirement. The way most of these businesses have their network set up, they'll have a router inside the store. The router is linked to a network video recorder, which is then linked to cameras, and that functions sort of like a CCTV setup. And then they have a point of sale system that they have plugged into a back office computer that's also linked into the router. Those routers are inaccessible from the internet at large. So we needed to develop a solution to get into that network and be able to export data out. So to get past that firewall, we sourced a device that we could ship on site. The device is able to run Elixir, and we can use it to find cameras on that internal network and push video streams back to the Savi cloud. We can also configure it to work with the internal only point of sale system APIs, and then forward those transaction data to the Savi cloud as well. The way the device talks to our main Savi API application is that when the device boots up, it initializes a socket connection using Phoenix channels to an independent device endpoint on the Savi API server. If the certificates on the device check out, the socket connection is then established and the device joins a specific topic based on the global unique identifier it gets assigned on provisioning. Phoenix channels are long-lived, so we really want to do our best to keep this connection alive, but if the connection does go down, the device is set up to attempt to reconnect indefinitely on a configured interval. So some services we want to retry the reconnection frequently, like video, where the data is heavier and it would take a lot to store it on that device. While others, for the transactions, they can store transactions locally between network losses, so they can survive hours between reconnections. Key to our implementation is the Phoenix endpoint. And the Phoenix endpoint, it requires a pub sub server to share channel state across nodes. Phoenix channels also have a function that can be used to broadcast to the connections, and you can use endpoint to broadcast to all your sockets that are connected to the endpoint. If you have a single server setup, you can also use a broadcast function on Phoenix channels, and the function contract is on this slide. Before Phoenix 1.5 came out earlier this year, the configuration was a little bit differently. Was set up a little bit differently. I generated a vanilla Phoenix app a few days ago just to show the differences, the current setup of the endpoint. So if you look at the config file, there is a pub sub server key. That's where you have to configure your pub sub server for the endpoint to use it. In application EX, you also have to start the pub sub server manually when the application boots. Before 1.5 came out, the pub sub server would start automatically, and the key has changed a little bit in the endpoint configuration. It used to be pub sub. So if you upgrade, you'll have to be aware of some of these changes. When we shipped all our devices out, we ran into some initial communications issues. The edge devices were all connecting to a single instance of a Savi server. As the servers are load balanced, it would pick one, connect to that. So we were getting data just fine, but our monitoring tools weren't aware of all the devices connected on all the servers. Our API server also auto scales, so we don't know how many instances of the API that will be out in the wild at any given time. And like I said, those devices connect to a single container. So in order to ping device updates to a specific device, we had to figure out what server that device was connected to and send the payload that way. Another issue we ran into, unrelated to the device, but we had some automated jobs. It would run as many times as servers that we had auto scaled at that point. So most of the time we only wanted that job to run once. For the rest of this talk, I'm going to cover the steps we took on the core server to address the communication issues with the device. I'm not going to cover our device-specific deployment or build strategies, as that device could be a conference talk in and of itself. Initially, all I wanted was for the app to cluster. Clustering can solve our inter-API communication issues, but after reading a lot of documentation, it seems like releases would be a great way to set the Erlang configuration needed for clusters and would allow us to give our nodes custom names and to be able to use EC2 security group firewall rules to our advantage. In order for clustering to be a little easier, we needed to implement a node discovery library for clustering. And then after we had all that complete, we need to verify that our app is actually clustered. So first off, releases. A release basically allows you to box up everything that your app needs to run. You can take the Erlang VM, the Erlang runtime, Elixir, your application code, and all the dependencies required to start the app, and it puts it in a single executable. There are a lot of benefits to using releases. First, mixed tasks provide command line tools for running operations, but they run outside the context of the app, which can make it tricky to test or to use with dependencies. Running functions that are built into the app can be much easier. And releases provide a lot of tooling for that. And Elixir applications, by default, they run in interactive mode, which lazy loads modules as you call them. This can cause a delay when the app starts before it is able to serve requests. Releases use embedded mode, which allows the app to serve requests as soon as it's booted up. Releases can also make running separate bits of an umbrella app easy for more of a microservice architecture. And finally, the one that we're most interested in, can specify virtual machine settings and node names so our app can dynamically cluster. We could do this with a combination of CLI flags, but this makes it easier to see what's happening. We can fill in dynamic values without needing to code a PR. There are a few downsides to using releases. It takes an extra little bit of configuration and requires separating runtime versus compile time configurations. We also need a build step, but we were using Docker, so Docker required a build step anyway. It was very easy to slot building a release into our Docker build step. Another thing to take note of is that builds need to happen on a host that has the same architecture and operating system as the target running the application. And it also needs to have the versions of Erlang and Elixir that your application requires. Again, we were doing that with Docker already, so it wasn't a big lift. Our application here is an umbrella, so it requires some extra configuration in the mix.exs file. A non-umbrella app can infer this and use defaults instead. Here we have two separate releases configured on this file. I copied this shamelessly from elixirlang.org. This just lays out how you name your release and set it up. If you see the application list there, the order of the application is preserved on boot as much as possible. They're defaulted to permanent, which means the node will shut down if the application terminates for any reason. Some other options are transient, which keeps the node up if the app terminates abnormally, and temporary, which keeps the node up even if the app terminates. You can bring in the application and not start it if you wish, or just bring in the application and not load it at all. If you have done a lot with supervision trees, the permanent, temporary, transient is conceptually similar to the restart strategy in a supervisor. Cookie here is for security on internode communication. If it's not provided here, a random one will be generated. We don't want to commit our cookie to source code, so we'll provide it in a different way, which I'll cover a little bit later. So setting the application config was probably the biggest pain point of converting a vanilla umbrella app to a release, especially one that has been generated a little bit older. We started our umbrella in 2018. Each app in the umbrella had a separate config folder with test, dev, and prod environments stored there. So to get this to work, we had to move every config into the root directory, update the config paths in the mix.css files to point to there, and also join all the environment-specific files into a single file, which required some diffing and some reduction of the scope of all the application ENVs that we have there. We also needed to separate out build time configurations from runtime configurations, as the standard environment config files are only loaded one time when the application is built. The file releases.exs allows for configs to be loaded at runtime, so any system.get.env calls can be placed there. We had some dev configs set up to pull environment variables from the system. So to get that to work, we had to re-import the releases.exs files in dev and then overwrite any ENVs that we had hard-coded in. Fortunately, in future Elixir 1.11 renames releases.exs to runtime.exs and preloads the runtime variables in each environment, as well as post-loading them in a release at runtime, which would help us in that scenario. Something else to consider with releases and the application at large is that mix is provided as a build tool with Elixir, but is left out in a release. The deprecated call here, you can see it commented out to use mix.config is replaced by import config, and any references to mix, for example, the mix.env call, need to be replaced. We got around this by creating an application env set to mix.env in config.exs, and we use that as a replacement for any environment-specific code guards. Next, we have more configuration. There's a release env file that comes with releases. It's a template file that is copied into every release, and they're executed on every command to set up environment variables, including specific ones to the VM and the general environment. It's basically a shell file for exporting ENVs. Some of the ENVs that are pretty important to the process are release distribution, which we set to name. It allows us to use long names instead of short names for clustering. That's important for EC2. Release node is the node name to use for distributed Erlang. A little bit more specific about the release node env. The short name for us ended up being a Docker container ID, which didn't allow us to cluster on EC2. So we had to use a long name, which is the release or the release name that you specify in your mix.css file, and a fully qualified domain name or IP address. So we ended up pinging one of the Amazon APIs to get the IP of the running host and injected that in as the long name. Another env in that file is the release cookie. It's the value that the distributed nodes use for authentication. We set that on the system in our env configuration file on Amazon, and then we re-imported it here to provide it to the release. The next file you need to work with is the VM-args EXS file. EX file, it is a template file that's copied into every release and provides static configuration of the Erlang virtual machine and other runtime flags. So you shouldn't set no names or cookies here. They should be set in the other file, but you can set all your Erlang virtual machine flags, garbage collection, distributed Erlang port range, and also specify TLS for your communication protocol. An example VM-args file, you can see at the bottom where we set the min and max ports used for the distributed Erlang, and also where we set up TLS. So are we done? Almost. We actually have to build it. So you can build it with mix release, and then it will build your binary in _build prod or whatever environment you're running on, rel, with your app name, your release name, bin, and then your release name as the binary path. We copied that bin directory into root in our Docker file, and we ran it with Docker start, with the bin start. So copying the bin into the root makes it easier if you need to SSH in to run commands via Docker exec. You can start your release with start, stop it with stop. It's pretty self-explanatory. The releases come with a few more functions for tooling. As mix tasks don't work super well and mix isn't pulled in with the release, what I would do where a script would normally be a task, I've converted them to Elixir modules that I run with RPC or an IEX. So you can run a remote IEX session by just calling remote with your release. You can type in Elixir code and run it with a command with the RPC, and that will run it in the current running instance of your release. You can also run your command in a new instance by using eval. It functions the same way as RPC. So we built our release. We were able to deploy it in that single binary. We were able to use a remote shell. It was great. We're all set up to start clustering. Clustering by definition is Erlang and Elixir or Elixir runtimes communicating with each other. Each runtime has a unique node, a unique name, and it functions as a node in your cluster. We took care of node naming, if you remember, with the release configuration in the release env and env.shell.ex. Something to note is that if you start a node with a long name and you try to connect another node with a short name, it won't work. Long node names and short node names are incompatible. You have to be consistent with all your nodes. When you start a distributed Erlang node, it also starts the EPMD service, which stands for the Erlang Port Mapper Daemon. It acts as a name server and tracks what node name listens on which address. All EPMD instances, they have to use the same port. So if you want to customize what port you use, you have to do it for all of your hosts that are starting EPMD. Your distributed nodes don't use EPMD for internode communication. They all have TCP IP socket connections to each other. And if you are on the host, you can call EPMD-names to get the names of nodes connected to the local EPMD instance. There are a few gotchas. So it runs on port 4369 by default. And like I said before, if you change that, you have to change it for every host that you have EPMD on. Implementations on Windows limit the node count to 60 on one EPMD instance. So that's about how many nodes you're limited to per host for Windows. EPMD connections are also not encrypted. So if your cluster is not firewalled correctly, you could be subject to man-in-the-middle attacks. And lastly, you might not even need it. So there are several strategies out there that you can build with an EPMD-less strategy. And there's some cool documents out there on the internet if you just search for EPMD-less. We're using AWS, as I said before, so there's some special considerations for AWS. If you're using Elastic Beanstalk for deploys, you have to map the EPMD port and the Erlang distributed port in your Docker run AWS JSON file. This basically allows you to point those ports from your internal container to the external host. And you also need to, in your AWS security group, add a self-referencing inbound rule so all your clustered nodes on different hosts can talk to each other. For node discovery, we started by leveraging a project called libcluster by Paul Schoenfelder. And it allows automatic formation of clusters with some minimal configuration. The config is super simple, which makes it great, easy to use. What I wanted to do was start with a local setup first to see everything working. So I went with this built-in strategy, the gossip strategy. And what the gossip strategy does is basically sends node names to the UDP address that other nodes are listening to. You can secure it here with a secret provided in the config. So I spun up 3 instances in Docker, and just scaled it up. And then I stuck a Nginx container in front of the whole thing so I could communicate with the cluster through a single address and port. And it worked great. I had the debug logs turned on so I could see all the internode communication. I could see them talking to each other. And I linked up one of our device clients to the cluster, and I was able to ping any one of the Docker containers and have it send configuration updates to that device. So it was great. Locally, no problems. I moved on to getting it ready for production. Luckily, libcluster is really great, and it allows you, if there isn't a built-in strategy provided, you can write your own custom strategy. Again, we were lucky we didn't have to do that. Kyle Anderson has created a library called libcluster EC2. It allows nodes to discover each other based on a configured EC2 tag. It does require a little bit of extra access. You need the EC2 described instances API endpoint, but it's pretty easy to do with an IAM policy. Again, the config here is pretty simple. App prefix here maps to the release name, which is used by release nodes as the first part, before the @ symbol as the node name. The tag and values are parsed out of the described instances EC2 API, like I said before, and it can be used to find the IP addresses of the nodes sharing the same tag and value. We went through a few different iterations of this where it looked like we were configured, but we didn't have the described instances policy set properly. We didn't have firewall rules set properly. So covering all those gotchas has got us to where we are today, where the app appears to be clustered. So with verifying the cluster, there's several different tools that you can have. What I did locally, I just viewed the debug logs. That might be kind of hard in a production or staging environment. So there's the node module, which allows you to use their functions to determine if you can actually cluster. So alive, arity0 lets us know if the current node is able to be connected to a cluster. Node list shows other nodes connected to the cluster. It does not show your current node that you're making the call from. Node spawn link takes a node name and function and returns a PID. It allows us to execute code remotely on another node. And if you've installed presence, presence lists channels that are connected and tracked. So results, success, we're able to verify that our app is clustered. And more importantly, we now have device status reporting properly on our admin page. You can see from the screenshot below. Before it was intermittently reporting off and online. Now it's online every time and with a device that we verified is connected properly. And we're also able to send configuration updates out to the devices on request. Some of the next steps that we want to take is to more heavily leverage Phoenix presence. We do use it a little bit for saving minimal state, so status, but we really want to track those channels a little bit better and also track the joins and leaves so we can determine if our network is pretty stable or not very stable. So we can maybe focus on some location that's having network issues, reach out to their IT teams. It could help us a lot there. By way of information, Phoenix Presence uses a function called conflict-free replicated data type, or CRDT. What that does is it guarantees eventual consistency. So all your nodes will eventually have the same state. You can do it a few different ways. You can send the entire state to each node, which could be pretty large from a payload perspective, or you could send every update to each node, which requires some guarantee in your communication layer. Another next step is the shared registry. I briefly mentioned that we had jobs running on every server every time that they got triggered. Luckily, the cron library Quantum already implements Swarm. It's also by Paul Schoenfelder. and it would allow us to start a job on only one server. They can tell that the job's already been started, so it won't try to start it again. I think I have a time for a few questions, if there are any.
Hey there. Thank you, Austin. This was orchestrating a fleet of edge devices, how Elixir releases and clustering lowers complexity. I don't see any questions right now, but if you could give us your information for people to be able to contact you if they have any questions about this, that'll be great.
Sure, yeah, I'm on the Elixir Slack. So if you want to reach me there, that's probably the easiest.
Perfect.
I don't know if there's any other Austin Hammers. If there are, then you'll be able to find me.
All right, that's perfect. Well, thank you very much for the talk. It was great, and we'll see you next time.
All right, thank you.